All right, seems like I'm here. All right, hello everyone. Welcome to the second half of the Math2521 and 2621 seminar. I guess first of all, can I just get someone to confirm that you guys are able to hear me perfectly fine? Just making sure that there's no technical issues. Okay. Um, yeah, all right. So I guess the sound is okay. You're able to hear me? All right, cool. Yeah, okay. I guess we can pretty much start. Yeah, so I guess like yesterday, for those of you who have watched the seminar, Felix and Wendy would have gone through most of the first half, and so here I'm just mainly dealing with the second half, or I guess really just the very last section. Um, yeah, so I guess like hopefully everyone's going well before the exam. I assume most of you aren't so familiar with this last section yet, but of course it's going to be weighted quite a bit in the final exam. Usually there's at least like one big question, maybe like one and a half that's on this section. And I think like based on last year, the 2621 exam at least was one of the hardest exams I have done. So yeah, hopefully you'll get well prepared for that. Okay, so yeah, the first one we're looking at is Cauchy's integral formula. I guess really this formula isn't actually that important because if you know how to use Cauchy's residue theorem, then that basically encompasses this. Like this question, you have to remember this particular form, but if you remember how to use residue theorem, you can do any question rather than using this. It's just a slightly stronger version. Um, but yeah, I guess you should still know this one in case there is an exam question that sort of gets you to, first of all, state this uh, formula and then ask you to use it. But otherwise, you would probably just remember the residue theorem most of the time. So this is saying that if we have some simply connected domain, so from yesterday, remember that simply connected just means that we don't have any holes in this domain. Then if f is a holomorphic function on omega, so if f is differentiable everywhere, then if we have gamma here being a simple closed contour, so remember that, oops, let me just change this. Yeah, so remember a simple closed contour means that it's, okay, so it means that it starts and ends on the same spot. That means it's closed, and it's simple meaning that it doesn't cross itself. So if this is my contour gamma, then it turns out that if I have one point here, so if I have a point W that's inside the interior of gamma, then I can evaluate this integral in this sort of way. This is typically saying if we want to evaluate an integral of this form, then all I really need to do is to sub in W into my function and multiply it by 2 pi I. Then I can evaluate this integral. So really this is just a method to handle integrals of functions that aren't holomorphic at a point. But as usual with all of the theorems, just make sure you're a little bit careful when you apply this. Like make sure all of these conditions are actually satisfied when you're applying it. Otherwise it wouldn't work. So it's important that like W here needs to be the interior. So like for example, if the gamma here is representing the unit circle, and then your W is like, I don't know, 5, then you can't apply this theorem because that's not inside the interior. So just make sure you're careful about it, that you actually exactly follows this, what this theorem here says. Okay, so we'll do a quick example on this, but again, like usually you'll be doing these questions using the residue theorem anyways, rather than just using this formula. But here we'll just illustrate how it works. So here we're trying to evaluate this integral. So here we want to make use of Cauchy's integral formula. So first of all, we just need to make sure that this actually satisfies these conditions that we have here. So first we need to make sure that the gamma here is a simple closed contour. So in this case, we just have the circle with a radius of 2. Okay, so that is in fact simple and closed. And then we need to see that the integral is in this form. So we have z minus w on the bottom. Okay, so z minus 1. And indeed, we know that the w, which is the 1 here, is actually inside the interior of this contour. And so this is fine. And so once we check that, we know that we can actually apply Cauchy's integral formula. So the function on the top, that's our f of z, and then we set our w is equal to 1. So all you really need to do is substitute directly into Cauchy's integral formula. So this is just Cauchy's integral formula rearranged to make the integral the subject, so we just multiply the 2 pi I to the other side. So the formula just says that we need to sub in w, which is 1, into the function, which is e to the z, so the exponential function. And so this integral is simply 2 pi I times e. Okay, so that's pretty simple. All right, again, as usual, I've fully mentioned this, but if you guys have any questions, just feel free to drop them in the chat. I will be monitoring that pretty closely, so yeah, I'll be able to answer any questions that you've got. Okay, so next section we have here is on Powerseries. So I guess Powerseries, we've seen a lot of them back in first year, but that was mostly in the real case, but now we extend it to the complex case, but it's more or less still the same. So a Powerseries is something that is of this form. So remember that the powers here actually have to be non-negative. If you have a negative power here, it's actually not considered to be a power series. Later on, we'll see that we've got things like the Lorentz series, which can have the negative indices. But this one has to be non-negative. Okay, so it actually turns out that we have some powerful results, which is that if you have a function that is holomorphic on this ball, so remember this means that everything that has a distance from z0 that is less than r. So this is the ball. So it turns out that we can actually write any holomorphic function locally as a power series, so about z0, and we can actually compute each of the coefficients in this way. I think practically you're not going to be using this formula all that much in exams anyway, but this is saying that we can. And what this also means is that this holomorphic function is actually infinitely differentiable. When we differentiate a power series, we can just differentiate it term by term. So I can with differentiate, I just need to bring down the power n, and then we have ncn. That will be the coefficient of w minus z0 to the n minus 1. Okay. Then next we look at Gauss's generalized integral formula. So it's generalized because the one earlier that we had. So in the previous slide, we had considered something where we have f of z divided by z minus w. This formula here is generalized in the sense that the denominator doesn't just have to be z minus w, we can have z minus w to some power, to the n plus 1. Okay, but otherwise the conditions are more or less the same as before. So we need to have a simply connected domain, f needs to be holomorphic, and the gamma here needs to be a simple closed contour. And finally, w is also in the interior. So if all of these conditions hold, it turns out that we can actually evaluate this integral. So once again, this is just a technique for evaluating some complicated integrals. If you get something of this form, then actually I can just use this formula to calculate it. This is one of the most useful theorems in this course. Again, like later on, we'll be looking at the residue formula, which is a little bit more general. In that case, we can look at cases where it's not just a single point W in the interior, but with other points in the interior as well, that will make it not holomorphic. Okay. So here we're trying to apply the generalized integral formula to evaluate this integral. So once again, the sign should pretty much be here, like we see this, we've got z to the n. Just by seeing this, then you might consider, okay, maybe we want to use Cauchy's generalized integral formula. And as usual, you want to make sure that the other conditions hold. It needs to be a simple closed contour, and w needs to be a point that's in the interior. So in this case, we have the unit circle. And so the unit circle, we obviously know that this is simple. It doesn't cross itself except the endpoints, and it's closed because it starts and ends at the same point. And in this case, our w would just be 0 because z is just z minus 0. So the bottom bit is just z minus 0 to the n. So based on the formula here, our w is actually the 0, and 0 is clearly in the interior of this unit circle. So once we've checked all of that, we can apply Cauchy's generalized integral formula. So that's saying that if I want to evaluate this integral, all I need to do is differentiate the function on the numerator. I just need to differentiate that n times and multiply it by, or I guess divide it by this. So that's all I really need to do. I want to differentiate the function in the numerator n times. Okay, so here this will be my f of z. That's the thing on the numerator. Or rather, I should say that's the thing that, like once I get rid of the z to the end of the bottom, this is the only thing left. So it's my 1. Okay, so if I want to do that, I just need to, so this is just using the formula. I need to differentiate the function n minus 1 times. It's n minus 1 here because remember the formula here was written with n plus 1, whereas in this case it's n, and so to adjust for that I need to have n minus 1 here. Okay, so this is just saying to evaluate this one, I just need to differentiate the function n minus 1 times, and depending on the value for n, we're going to get a slightly different answer. So n is just any integer, so we're going to get different answers depending on which integer n is. Because obviously if n is 1, so if n is 1, then that's saying that we have to differentiate it 0 times. If you differentiate the function 1, if you differentiate this function 0 times, then it would still be 1. So this guy will be 1, and then this thing here on the bottom would be 1, and so we're left with 2 pi I. But on the other hand, if n is greater than 1, so if n is greater than 1, that's saying that we need to differentiate at least 1 time. So like if n is equal to 2, that means we have to differentiate once. If n is equal to 3, it means we have to differentiate twice, and so on. But we also know that when we differentiate 1, we just get 0. So if we differentiate f, we just get 0. No matter how many times we differentiate it, we'll always get 0. So if n is any value that's larger than 1, then we have to differentiate this function, and that's just going to give us 0. Okay, now that's actually just considering n being a positive integer. We haven't considered the case where n is a negative integer. But actually you have to be careful here, because if n is a negative integer, well, obviously something seems to be wrong. Because actually 1 over z to the n, if we imagine n is negative, then actually this thing is just entire. Right, let's just have an example. Like let's just say n equals to negative 1. Well, if n is negative 1, this is actually just the integral of z. Oops, not that. But yesterday, Wendy would have talked about Cauchy's Gauss, which is saying that if we have a function that is entire, or I guess really just a function that is holomorphic on this domain, then this should be 0. And in fact, this would be true for any n that is less than or equal to 0. You would end up with something that is just holomorphic on the unit circle, and so when you integrate this would be 0. Okay, because actually the function here is holomorphic at 0. It's only when n is larger than 0 that we start having issues, where this function is not holomorphic at z equals 0, and we need to apply Cauchy's generalized integral formula. But if the function, if it is holomorphic at 0, like in this case, then well, it's just 0. All right. Okay, so I guess like this next question is a little bit harder. I think this question is pretty common. You've probably seen it before. I think this has come up like twice in the past papers, and also like in the tutorial problems as well. So yeah, I guess sometimes they're not very creative questions. They just reuse the same one. But okay, so this is a little bit more difficult though. So here I want to show that if f is an entire function, so again, entire means that it's holomorphic on the entire complex plane, and we're also given this additional fact. Then we want to show that the derivatives, or the higher order derivatives evaluated at 0 are all 0. Okay, so I guess like when you see this you might not immediately know what you're meant to use. I guess it's a little bit difficult to see. I guess the hint is maybe just by seeing the fact that we're trying to look at this guy. So we're trying to find this. And I guess once you see that, you might start thinking of Cauchy's generalized integral formula, because that gives us a formula for the kth derivative evaluated at 0. Right, so this is the case where w is equal to 0, so we sub in the 0 over here, and down here we don't have anything left. Okay, so Cauchy's generalized integral formula gives us this. So now I need to somehow show that this is equal to 0, which I guess is still not so clear how we're going to do that. So I guess when you see this in your exam, what you should be thinking of is how can you use this hint? Because obviously we somehow need to use this. So somehow I need to show that this thing here is equal to 0. Well, I guess if we're looking at the modulus here, it seems like maybe it would be better if I consider the modulus of this function. Because first of all, we know that the modulus is already non-negative. And so that just means that I actually just need to show this thing on the right is 0. Maybe that's not so hard if I make use of this condition. Okay, so here's where you have to be a little bit creative. So first we'll note this one. So where does this come from? So we're just looking at this integrand, and we're actually saying that the modulus of this integrand is less than or equal to this thing on the right. So the top part is just using the given inequality, because we're saying we're given this thing about f of z. So if I just do that on the numerator, I will get the modulus of z plus 1. Okay, so we have this. So this is where we've made use of the condition. Now, I actually say, so Wendy would have gone through this yesterday, where we're saying that, so the ML lemma would say this. Oh, is it still not working? Okay. Okay. Never mind that. Sorry about that. Yeah. So I guess essentially, if we're trying to apply the ML lemma, what we're saying is that this should be less than or equal to the length of this contour. This contour can be whatever I choose, multiplied by the supremum of this modulus. So it's the length of the contour multiplied by the supremum of this of the thing inside. So I want the maximum value of it. So in this particular case, I have chosen the contour to just be the circle centered at 0 with radius of r. And so in this case, the length of this contour would be 2 pi r. That's just the length. That's just the circumference of this circle. And the second thing here is from here. So this is the supremum of f of z divided by z to the k plus 1. Okay. Yeah, I think I was lagging a bit earlier because I think I had some internet issues, but I changed my I changed my phone hotspot, so yeah, I think it should be a little bit better now. But I think OBS is telling me that I don't have any drop frames. Yeah, I guess if there's more issues in the future, just let me know so I realize. But yeah, so essentially we want to find the supremum of this, but because I have chosen this to be the circle centered 0 with a radius of r, then actually we know that the modulus of z is just going to be r, because I've chosen this to be the circle. And so basically by choosing it to be a circle, I can very easily just calculate this supremum, and I can put it in. So I can replace the modulus of z with just r. That's what this thing is. Okay, and then we do some basic cancellation, and we arrive at this. Okay, so I guess now it sort of becomes like a first year question. So we know that the modulus of this thing is bounded between 0 and this expression on the right. And so all we really need to do is see what happens when we take r to infinity. Well, clearly if k is greater than or equal to 2, then this thing on the right here is going to go towards 0. This is from first year calculus. And so from the pinching theorem, we know that both the lower and the upper bound have a limit of 0. So it follows that the thing in the middle must also have a limit of 0. But we know the thing in the middle shouldn't depend on what r is, so it should just be 0. So the modulus should just be 0, and hence, I guess we can also conclude that it's just 0. Okay, so I guess like maybe some of the steps in the middle weren't completely clear. So like quite often, if this is what you want to do, so you want to show something is 0, but you know it's equal to this. So a common technique is for you to come up with some sort of contour. So in this case, like the question never tells us that gamma has to be the circle with radius r, but I think after you do a couple of questions, you will find that it's very common. I feel like maybe like 90% of the time when you see a question like this, the contour you're going to consider is probably the circle with a radius of r. So maybe the first time is not clear, but after you do a couple of times, every question is the same. You pretty much always want to choose the same contour. Of course, sometimes I guess for harder ones, you might need to be a bit more creative, but usually this would do. Okay, so I guess now we have shown, okay, so we know f is entire, so we can write it in this form. This is just the power series expansion. So because it's entire, we are sure that we can write it as a power series. But just from before, we already know that Cn is going to be 0 for n greater than 2, or greater than or equal to 2, because we know this thing here would be 0 for n greater than or equal to 2. So in other words, that's saying that all we have left is C0 and Z1Z. So actually, the second part of this question, which I'm not going to scroll back up, but the second part of the question is just for us to show that C0 and C1 are both less than or equal to 1. That's what the second part of the question wants us to show. So, okay, so C0 is equal to the modulus of f of 0. So how did I actually get these inequalities? Well, actually, this was from the previous slide. So this statement here, this is actually true. Oops. This is true for k greater than or equal to 0. So actually, this is true for k greater than or equal to 0. It's just that for k greater than or equal to 2, we know for a fact that it's actually 0. But even if k is 0 or 1, this inequality here is still true. And so I can actually use this to help me establish an upper bound for fk0. So that's where this comes from. So in the particular case where, so here we'll have k is equal to 0. So if k is equal to 0, then, okay, well, k is equal to 0, that goes away, that goes away. Actually, hang on. Did I do something wrong? K is equal to 0. Okay. Okay, right. So k is equal to 0 is fine because we already know that we already know this is true. So we're actually subbing directly into here. If I'm subbing in f of 0, we know for a fact that f of 0 is in modulus is less than or equal to 0 plus 1. And that's just directly using this thing that we're given. Okay, and so we already know that C0 is going to be less than or equal to 1. I guess the other one thing we want is C1. In this case, we're going to use the formula that we derived earlier, which was this. So here we can say that if k is equal to 1, then we can say f of 1, I guess that's just f dash 0, is going to be less than or equal to, if I sub in k is equal to 1, we will get r plus 1 divided by r. I just realized there shouldn't be an I here. That I is a typo. Okay, so essentially what we found here is that f dash 0 in modulus is bounded by r plus 1 on r. That's where this comes from. But we also know that as r goes to infinity, this thing here obviously goes towards 1. And so in other words, we're saying that f dash 0 is actually bounded above by 1. And so we can obtain this, and that completes what we tried to find. Okay. Then we have some other theorems. We're not going to talk about these much. I don't think these get assessed very much. But essentially, it turns out that if f is bounded and entire, then f is constant. So remember, f being bounded just means that f of z is less than some sort of value. Okay, so and it's entire, so it's differentiable everywhere. It turns out that it actually has to be constant. This is a pretty interesting result. I think you would have looked at this result somewhere in class. You would have seen the derivation. I think this one has actually been asked maybe once before, but I don't know. I feel like it's something they would avoid asking in the exams nowadays because people can just look at the lecture notes and just copy down the proof. So you're probably not going to get that proof. Okay, and then secondly, this other theorem is saying that if f is continuous and this integral is 0 for every closed contour, then f is holomorphic on omega. So essentially, this is the converse of the Cauchy-Gaussat, because Cauchy-Gaussat says that if f is holomorphic on here, then for every closed contour, the integral will just be 0. So it's very clear this is just the converse. Practically, I don't think you're going to be using this theorem very much, mostly because you need to use every closed contour. I think that generally it's quite hard to write a proof involving every closed contour, so this is usually not very useful. But yeah, I guess it exists. Okay, so then there's the power series stuff. So I think this slide is mostly just first year. So first year you saw power series, but that was in a real variable. But here now we're looking at complex expressions. But essentially it's exactly the same idea. So this is a power series. Once again, I'll emphasize that power series don't have any negative powers. All of these are non-negative. N is non-negative here. Otherwise, it's the same. So power series don't necessarily converge. So we have a radius of convergence, which just like in the real case, we're talking about the largest r that's positive, such that this thing here converges in the ball. So I guess like in the real case, we'll be looking at whether it converges in some sort of interval. Like maybe we would say, yeah, like some interval that it converges in, like maybe z0 minus r, z0 plus r. Right, so I guess in the real case, we're looking at some sort of interval where it converges. So we have like this radius of convergence. But of course, in the complex case, we don't just have like a positive and negative direction. We have like infinitely many directions. So we're talking about convergence in this ball. So on the complex plane, maybe we have a z0 somewhere. We're talking about convergence in this circle of radius r around z0. Okay, so if this power series actually converges everywhere in this ball, then the largest r would be the radius of convergence. If it only converges at z0, then we say r is equal to 0. And if I guess if it converges everywhere, then we say r is equal to infinity. Okay, and the nice thing is that the power series can be integrated and differentiated term by term inside. I guess like that's fairly intuitive, but it's a very useful result. Okay, now I think usually power series are also pretty common in exams. There's usually like one of these in every exam. I think this is one of the relatively easy parts. So in this example, we're given this power series. And so the first part is to find the center and radius of convergence. So the center is usually just a free mark. You just look at here. this is clearly a power series that that's centered at -3. So essentially, we're just looking at like where is this thing 0. That's when z is equal to -3. So that's our center. So I guess that's a free mark. Then second thing is the radius of convergence, which is sometimes a bit harder to calculate. I think most of the time in this course at least, you'll be calculating the radius of convergence using the ratio test. So based on the ratio test, basically we're letting an be each of these terms. So by the ratio test, what we're looking at is the ratio of two consecutive terms, so an plus 1 divided by an, and we're looking at what is the, okay, and in order for it to converge, we want the limit as n goes to infinity to be less than 1. So if I just sub in an plus 1 divided by an, and then evaluate the limit as n goes to infinity, then I will get the modulus of z plus 3. So we know that this power series would converge if this is less than 1. And so we're saying that I should say radius, the radius of convergence would just be 1. Or if this, or I guess in some other cases, some other example, maybe you have z plus 3 divided by 2, then in that case, the radius of convergence would be 2. I guess it's important to note that when we say radius of convergence is 1, we're just saying that we are sure that if we are within this circle, it will converge. But actually, if you are on the circle, so if this ratio is exactly 1, we don't actually know whether it converges or not. It could converge or it might not. Like just like in first year, we say that the ratio test is inconclusive if it's equal to 1. But usually in this course, we don't have to worry about it. We're only looking at this radius of convergence. We're not concerned with whether it actually converges when it's equal to 1. Okay. So the second part of the question was to find an expression for h as an elementary function. So I guess even though this is a complex analysis question, but this is very similar to just questions you might see in first year. So this just means that somehow I want to evaluate this sum. So I want to somehow find this as a nice elementary function rather than as a sum. So usually there's just some trick to it, which is exactly what's happening here. So it turns out that this is a nice way to evaluate a sum that is of this form, is that if I first take out z plus 3 from the sum, then this thing here is quite nice. Because it turns out that this thing here you might recognize is just the derivative of z plus 3 to the power of n. Okay, so pretty much like we can rewrite it like that, and then we would assume that we can just interchange the derivative and the summation. So if I interchange it, then I will get this. And then we all know that when you sum this series, we will get this. Because if we sum r to the n from 0 to infinity, we should get 1 over 1 minus r. Okay, so we'll get this, and then we can just simplify it and differentiate, and you'll get this final answer. Usually this thing is a bit more straightforward. And finally, the last question is like, where is h analytic? So when we say analytic, that's just saying like where can we represent h as this power series? So we already said that this power series is centered at -3 and it has a radius of 1. So this is the center. So the center, and this is the radius. So that's really simple. Okay, and I guess like here we have another very similar example. So I guess like last time we had the n in front, but this time it's 1 over n. So it's just slightly different. But before I go through this example a little bit more quickly, because it's fairly straightforward. So find the center and radius again. So the center is once again a free mark. You look at here, where is it 0? We're at 0 when z is equal to -1. So that's the center. And in terms of the radius, it's a little bit more work, but it's same as before. We just want to use the ratio test. So we let an equal to that term, and we look at what happens as n goes to infinity for this ratio of an plus 1 over an, and it turns out that it equals to the modulus of z plus 1. And based on the ratio test, we know that it will converge if this is less than 1. And so once again, we just have a radius of convergence being 1. Because this thing here is just a circle centered at -1 and a radius of 1. So circle centered at -1 with a radius of 1. So this is saying that in this circle over here, this power series would converge. And outside of this circle, the power series would not converge. Okay. The part B of the question was to write down a power series representing f dash z, so the derivative. So the important thing to remember from earlier is that when we have something in a power series form, it's very easy for us to differentiate or integrate. All we really need to do is to differentiate or integrate it term by term. So if I want to differentiate it, I just need to differentiate it term by term. So differentiate the thing inside, that's very simple. If I differentiate it, I will get this. The n will cancel out in front, and this will be n minus 1. And I guess like for convenience, I'll just re-index it. So it starts from 0 and goes to infinity. But these are just the same thing. I've just re-indexed. Okay. So the first part of the question is a little bit more complicated. So the third part is to find an expression for f as an elementary function. So well, I guess like the fundamental theorem of doing exam questions is to say that you should always watch out for the previous parts. There's probably a reason why they gave you a part A and a part B. Like there's probably a reason why they asked you to write this thing down. They probably didn't do it for fun. So for part C, you should just be thinking of how do I use part B. If you don't use part B, then maybe you'll have a tough time. But okay, that's what we should be doing. So in part B, they made us find f dash z, and it equals to this. And at this point, you should realize that, well, f dash z is actually very nice. This is a very nice expression. Because this is simply, whoops, this is simply 1 over 1 minus z plus 1. Because once again, this is just a geometric series. It's a geometric series, so I can actually sum it up, and I get this very nice expression for it. Okay, so actually f dash z is -1 over z. But that means that now we can just integrate both sides. So if I integrate f dash z, I will now get f z. If I integrate -1 over z, I will get negative log of z. Most of the differentiation integration for complex numbers works in very much the same way as the real case. And we need to add a constant. So the thing to be careful here is note how I have used log 0z. So normally the log that you use, so normally it will be the one that has a branch cut on the negative imaginary and negative real axis. Like normally this is where the branch cut is. This is where the log is not continuous. But in this particular question, we actually need to make sure that we don't choose that branch. Because in this question, we're actually told, well, not told, but like we already worked out that this function here should actually converge on the circle on this circle that I drew earlier. It should actually converge on this circle. So if I were to if I were to use the normal logarithm, the normal complex logarithm, that wouldn't work because it's actually got the branch cut on the negative real axis. So in this case, I'll need to choose another logarithm. It doesn't really matter, but in this particular case, for convenience, I've just chosen log 0. So this is the logarithm with the branch cut being the positive real axis. And so it doesn't touch this other side. Okay, but other than that, all we really need to do is just find the constant and then we're done. So as usual, to find a constant, I just want to sub in some sort of value and evaluate the constant. So I just need to have a nice value where I know what f of z is. Well, as usual with power series, if I sub in z is equal to -1, so if I sub in z is equal to -1, this thing here would be 0, and it's gone. And all of these terms will be gone. So we actually know from this power series expression that f of -1 is actually 0. Okay, so if I sub in -1, like this, that will equal to 0, and now I can very easily find c. So c is in fact just I times pi. So I sub the c back in here, and my f of z is negative log of z plus I pi. Okay, and now we are done. Okay, yeah, so I guess extending on with what we just saw, so Taylor series, again, this is very, very similar to the first year case. First year we look at the real numbers, but now we're looking at the Taylor series with complex numbers. But we see that this thing here is pretty much the same. This is the same formula that you see for the real case, except instead of having it evaluated at real numbers, now they evaluate it at complex numbers. And just like before, the Maclaurin series is the one centered at 0, but of course you can have it centered at different values. So you're expected to know common Maclaurin series like the exponential or the sine x from first year, so how the exponential is x to the k divided by k factorial, where k goes from 0 to infinity, etc. Here you're meant to remember these. But I guess like if you are treating this exam as an open book exam, then yeah, I guess that's not so much of an issue. But yeah, but you are meant to remember those. Okay, so yeah, this example we have here is still fairly simple. So determine the Taylor series of this one. This is really just a first year question because even though this is complex numbers, it works in exactly the same way. So I guess like if you get some like completely random new function, and then you'll probably need to use this formula. You need to calculate the derivatives, and then hopefully you can find a pattern, and then you can write it like this. But more generally, you probably don't need to evaluate the Taylor series from first principles. More likely, it's already in terms of functions that we already know. So in this case, it's in terms of functions that we already know. Because we actually already know how to write the power series, well, I guess the Taylor expansion for the exponential. So there's no point deriving this from first principles. In fact, that would be a big mess. It would be quite horrible. It's much easier to actually just use the formula for the exponential that we already know. We just put it in, and then pretty much expand. So this is just to expand, and then all we've done here is we have reindexed. I've just reindexed it so that the z is to the power of k, so that now I can compare them. And I've just put them all together now. I've just factorized out the z to the k. So that should be fairly straightforward. So now I have gotten the Taylor series for this new function that we have, but these are the coefficients. Okay. So I guess the thing that is relatively new to this course would be the Lorentz series. So this is usually if a function is not holomorphic at a point. So so usually in this case, like we can't have a single, well, I guess like you can't use a power series to describe the whole thing because there are points where it is not holomorphic. So typically the way we look at it is like this. So okay, so typically what we do is we look for these sort of, oh, sorry, that's the wrong thing. Okay, so I guess like the only difference between the Lorentz series that we see here and the Taylor series that we saw earlier is that, well, here we also have these negative indices. So before I emphasized how for power series we always just have non-negative powers, but actually in here, in these cases, we can actually have negative indices. So our summation actually goes from negative infinity to positive infinity. Of course, some of these coefficients could be 0. And just like before, you can actually calculate these coefficients in this manner. But I think, again, practically you don't do this too often, but you could. Okay, so yeah, so usually we'll talk about a Lorentz series on an annulus. So this is just saying if we have a point z0, what this a here represents. Oops. Okay, this should be dotted. So this region that is in the middle here. So essentially for Lorentz series, we actually need to have a Lorentz series on a particular annulus. So like for example, this part that is between the two circles, we can define a Lorentz series over here. You could define another Lorentz series that would be the inside, so inside the first circle, or you could have another Lorentz series that would be on the outside. So actually, you would have 3 different Lorentz series depending on where you're interested in. So if I'm interested in having the Lorentz series converge in a point that's outside the two circles, then I'll need to use another Lorentz series. Whereas the current one that I have written, where I've shaded, so this Lorentz series would only converge within this shaded region, but it wouldn't converge inside the inner circle or outside the outer circle. I think it makes more sense if we look at an example. So probably this one. So usually you might see a function like this, and they ask you to find the Lorentz series in this annulus. So let's just draw this out. So there are obviously 3 points here where there's issues, which is when z is equal to 0, when z is equal to 1, and when z is equal to 2. So it's 0, 1, 2. So these are the 3 points where we have issues because f of z here is not holomorphic at those points. So I guess here where, okay, I guess like here we're actually trying to find the Lorentz series about 1. That's pretty much what this is implying. So, okay. I guess again that should be dotted, but I'm not bothered to fix it. So essentially the question here wants us to find a Lorentz series for this function that converges in this region that I have shaded. So because there are issues at 0 and 1, at 0, 1, and 2, so this is saying that I actually have, if I'm interested in this converging on the inside, I'll need to have a different formula compared to on the outside. So whenever you get these questions, you always want to like first draw a diagram to sort of see like which part you're looking at. So here I actually wanted to converge on the outside of the circle because you actually get a different series, or you have to do your working out in a different way. So we're trying to find the outer part. And so the series that we end up finding is not going to converge on the inside, it's only going to converge on the outside. But then how do we actually find it? Well, actually this algebra here is really bad. There's quite a lot of stuff in here generally, right? So, okay, usually the first step to do is partial fractions. So hopefully you remember how to do this well from first year. So if I do partial fractions, believe me, it would break up into this. Okay, so I guess like this term is already okay. So essentially we're trying to get something that is of the form z minus 1 to the power of n, where n can go from negative infinity to positive infinity. So trying to find this Lorentz series. So we know that it has to be centered at 1 because we are trying to get one that converges in this shaded area. And so here I want it to be centered at 1, as opposed to being centered at 0 or 2. So basically I want to get it into this form. So this term itself is already quite nice. This is already in the form I want, but the other two are not quite. So here we need to do a bit of like some algebraic manipulations in order to actually turn these ones into z minus 1. That's what I want to do now. I want to turn these two other ones into z minus 1. Okay, So this is some ugly algebra, but let's try to look at this one. So from the previous slide, this was 1 over z. So here you might be wondering, like, how do I get from 1 over z to this thing? Well, I guess like if you imagine this, what I'm doing is I am taking out 1 over z minus 1, and then to compensate for that, I will need to divide by z minus 1. But then here, if you very quickly just manipulate this fraction, I can do z minus 1 plus 1. Then you end up getting this thing here. So I think you should recognize this trick because you will need to be doing the same thing if you get this sort of question in the exam. So if I have a denominator that is not what I want, so if it is z instead of z minus 1, then this is the trick that you want to throw, which is you want to take out the z minus 1, then inside here, it will become like that. Okay, and do the exact same thing with the other fraction. So this fraction was earlier, it was z minus 2. So what I want to do here is I want to take out the z minus 1. Then this thing here would be z minus 2 divided by z minus 1, and which is just this string on the bottom. And so again, I have been able to convert everything in terms of z minus 1. So now this looks, well, I wouldn't say nicer, but this looks closer to what we're trying to get. Because we're trying to get it into this form with z minus 1 to the n, and not z or z minus 2. So actually, just by using this trick here, I have converted it so that everything is z minus 1. Okay, and then well, more things you can do. So, oops, let's just look at this one. Now this thing is actually in the form of 1 over 1 minus r. So we know as usual that if you have something of this form, 1 over 1 minus r, then we can actually write this in terms of a summation here. But this is just a geometric series. So this thing is in the form of 1 minus r, where r is equal to negative 1 divided by z minus 1. That's how we get from the thing I have circled, that's how I've gone from here to here. But one thing you have to be careful here whenever you do these questions is you have to remember where are we actually looking at it. So we are looking at it in this region where z minus 1 modulus is greater than 1. Right, you have to keep this in mind. Z minus 1 modulus is greater than 1. So here, the common ratio that we talked about, the r is equal to 1 over negative 1 over z minus 1. And because we know this is true, okay, I guess so we want this to be true. And so this one actually, this modulus here would be less than 1, which is what we want. Right, so that's important. This is important because now, because this means that the series that we get is going to converge in this region that we want. Whereas on the other hand, if you wanted it to converge in the inner circle, so if I wanted to converge inside here instead, then we need to do a different method. In that case, I would rewrite this thing as, so I would rewrite 1 over z as 1 over z minus 1. Oops. What do I need? 1 plus. Right, that's very important. So if I'm only interested in if I'm interested in converging inside the circle, so inside the circle z minus 1 modulus less than 1, then this is how I would do it. I will rewrite 1 over z like this, and I will write this as a power series. Negative 1 to the n, z minus 1 to the n. z minus 1 to the n. So in that case, this thing here would converge inside the circle. But because in this question we're trying to get it to converge outside the circle, I didn't do this. What we did here was this other technique instead, where we have the 1 over z minus 1 as a ratio, because in this case, this is less than 1. And it will converge outside the circle, which is what we want. Right, hopefully everyone caught that, because I think that's pretty confusing. So depending on where you want it to converge, you actually need it to be a little bit different. In some other even trickier questions, I don't know, maybe we want to converge it. Maybe you want to converge inside this region. Again, with dotted lines, I just haven't dotted them. In this case, you might need to use different techniques. For some of them, you might have to use this technique, and for the other ones, you might have to use this technique. But in the end, the goal is just to make sure that whenever you are converting these fractions into this sort of sum, you have to make sure that it's actually converging in the right place. So you want the ratio to be less than 1 in modulus in order for it to actually converge. So always check this. Okay. Yeah, otherwise I think this page is a bit of a mess now. Okay, so otherwise so you do that and we get up to here. And now if you watch closely, actually we can rewrite it with these coefficients. So if n is even here, if n is even, then we'll see that the first term is actually the same as the third term. But if n is okay, sorry, so I've got the question in the chat. So our goal with our Lorentz series is to do some manipulation until we get stuff in the form of 1 over 1 minus r, where r is less than 1. Yeah, so I guess that is part of it. Yeah, so not only do you want it to be like that, but you also need to make sure that the r that we have is either z minus 1 or 1 over z minus 1. One of those. First of all, you have to make sure that it's actually centered where you want it to be. And after that, yeah, either 1 or 1 minus, either r being z minus 1 or 1 on z minus 1, whichever one gets it to converge in the area that you want. Yeah, so 1 on z, there's two different ways I can write it. I can either write it like this one on this page, or I can write it on like the one on the second page. So both of these would end up giving you a series in terms of z minus 1, in terms of powers of z minus 1, but one of them would, so the one on this page would converge in the region z minus 1 greater than 1, which is outside the circle, whereas this one that you have here would converge inside the circle. So this is inside. Well, I guess not this converge. I mean when you convert this into a series. And yeah. So I guess otherwise, this one is just to simplify it down. If we see that n is an even number, so when n is even, actually the first term and the third term are the same, and so then the coefficient is actually just 1. The reason why these are odd numbers rather than even is because we have an additional one outside. So when n is even, actually the coefficient of z minus 1 to the or this n here is actually odd. I think this is a bit confusing because of the notation, because the n in here is not the same as the n in the second equation. So they're different n's. But yeah, I guess it becomes a bit more clear if you write out a couple of terms. Okay. So let's see. All right. How are we going for time actually? Okay, I think I've been going too slow, but I guess that's fine. Okay, so I guess in case anyone's still not fully clear about the Lorentz series, here's another example. So here we are trying to find it in terms of powers of z minus 2. So basically, I want to have a Lorentz series that is centered at z is equal to 2, and I want it to converge at z is equal to I. So once again, you should draw out a diagram and look at where you want it to be. So this is 2, and then these are the problematic points. This point and this point, these are the problematic points. So 2, 4, and then negative 2i. And we want to find it here. Okay, so what I mean by problematic points, basically I'm saying we can have this one, and we have the second one. So depending on where we are looking at, we are going to have a different Lorentz series. So I would have a Lorentz series for the region inside. I would have another Lorentz series for, oops, got rid of too much. I would have another Lorentz series for the thing that's in between the two circles, and I would have a third Lorentz series for the region that is outside. So depending on where it is, I would need to have a certain Lorentz series. So the question wants us to find the one that converges when z is equal to I, which is over here. Clearly from this diagram, I is something that is between the two circles. So actually the question here is really asking me to find the Lorentz series that converges for z minus 2 between 2 and root 8. Right, you can see that the inner circle is the one that has a radius of 2, and the outer circle has a radius of root 8. So I lies in between those two circles. So if I want this if I want this Lorentz series to converge at z is equal to I, it means that I want to find the series that converges in here. And so once again, we're actually doing the same thing as in the previous question, where I'm trying to manipulate these two fractions so that first of all they are centered at 2. So I want to make sure they are centered at 2. And secondly, when I convert them into the sum, I make sure that each of the common ratio is something that is less than 1 inside this region. So I want it to be less than 1. So let's take a look at how we do this. Okay, so we aim to find the Lorentz series inside here, which is what I drew on the last slide. Okay, so here we are going to go through some very similar tricks. So this is exactly what I mentioned earlier, right? So here actually we're looking at the region in between. So actually for these two fractions, we're actually treating them in two different ways. There's two different tricks. So for the first one, I am manipulating it so that I get something of this form. Like notice how the z here is like on the numerator of this fraction, whereas in the second case, the z is actually on the denominator of this fraction. Because in each case, the reason why we manipulate it like this is we have to make sure that the ratio, so z minus 2 divided by 2 plus 2i, oops, 2 plus 2i, so this is equal to z minus 2 over root 8, and I want this to be less than 1. Okay, so what we have actually, so like the reason why we have done this is that if you have z minus 2 divided by 2 plus 2i, this would converge when the modulus of z minus 2 is less than root 8. And that is what we want. Because we want it to be in the middle here. In this region, we want it to be less than root 8. So that's why we have manipulated in this way. if instead you want it to be outside that big circle, you would have manipulated it so that it's in the same form as this one. So I guess to summarize a little bit, like for this one on the right, we have manipulated like this because this would actually be greater than 2. So basically you want to rewrite these two sums, you want to rewrite these two fractions as a sum, but you want to make sure that these sums actually converge in this region that we want. So you want to make sure they converge in this region. And to ensure they converge in this region, that's saying that you need to make sure that this thing, which is r, has a modulus less than 1. And so it's very important, like why we have manipulated them in two different ways. But otherwise, like once you get that, all you need to do is convert these into a sum, which is what's happened over here and over here. And essentially, this is the Lorentz series that we get. And this should converge at I. Okay. So all that's left is to actually just say like this f of z is in the form of a Lorentz series. And if you look at it carefully, these are the values for the coefficients. Yeah, basically I just check the terms. Pretty much like these ones are all the non-negative terms, and these are all the negative terms. It's just been rewritten a little bit to put it into this form, but I don't think you really need to. You can keep it in this form and it's fine. You can keep it like this and your lecturer should be okay with it. Okay. Yeah, then we have this is, I guess, one of the last sections, but there's lots of questions on this, which is singularities. So an isolated singularity is a point for which f is holomorphic on the open ball, but it's not differentiable at z0. So this is saying that z0 is a singularity if f is differentiable everywhere around this point, but f is not differentiable at this point specifically. And so there's different types of singularities. One of them is removable singularity. So I guess that you see a lot of these in the real case, like maybe something like sine x over x. And you've probably seen something like this. So like sine x over x is not differentiable at 0 because, well, it's not defined at 0. If it's not defined at 0, it can't be differentiable there. But we realize that if you were to replace, or I guess if you were to redefine the function so that when x is equal to 0, we define the function to be equal to 1, then you actually find that, well, now it's okay. For example, the function is now continuous. Okay, so it's very similar in the complex case. So sometimes maybe there's just a point missing. If you put it back in, the function is now perfectly fine, as in it's now differentiable everywhere. So that's a removable singularity. Then the second thing we have is a pole. So so one of the ways of looking at these is to look at the Lorentz series. So we have a pole at z0 if there is some non-zero but finite number of n less than 0 that have coefficient non-zero. So this is saying that if I were to write out the power series, not power series, if I were to write out the Lorentz series of this function around this point, it would have a finite number of coefficients for the negative powers. So maybe if I have something like z to the negative 1 plus z plus z cubed plus dot dot dot. So let's just say this is my function, and this function would have a pole of it would have a pole at 0. It has a pole of 0 because there is a finite number of coefficients that are not 0 for negative powers of z. So this is a negative power of z, and its coefficient is 1, so its coefficient is not 0. but it's a finite number because all of the other z's with negative indices have a coefficient of 0. So this is actually a pole at 0, and we'll say it's a pole of order 1 because there is only, let's talk about that next. But yeah. And then finally, if something has got infinitely many non-zero coefficients for the negative indices, we will say it has an essential singularity. So I think the most typical example you see for this is something like 1 over e to the 1 over z, because we know that this is equal to 1 over k, 1 over k factorial. Okay, I think my Mac is not handling this very well. My Mac is slightly dying, but okay. So essentially we get this. So we know that the exponential of 1 on z is equal to this, and here we actually have infinitely many non-zero coefficients for negative indices. Because k here goes all the way to infinity, so they're saying that we have 1 over z, 1 over z squared, 1 over z cubed, and so on, and all of these have a coefficient of 1 over k factorial, which is obviously not 0. So it has infinitely many non-zero coefficients for the terms of negative indices, and so we say that it has an essential singularity. The difference between like the pole and the essential is that one of them has a finite number and the other one has an infinite number. It turns out that these three are exclusive and exhaustive, so meaning that something can only be one of these, and something has to be one of these. It can't be, if it's isolated singularity, it's automatically one of these. There's no other cases. Okay. So, usually if you want to work out what sort of singularity it is, so first of all, if the limit itself exists, then we have a removable singularity. So just like the sine x over x, we know that the limit as x goes towards 0 actually exists, so that will be a removable singularity. So this is saying that if you just redefine the function for that certain point, then it will exist, then it will work, then it's a removable singularity. So this is usually a small problem. You can just like redefine the function to exist at that point, then it's okay. Whereas on the other hand, we have a pole. If the limit itself doesn't exist, but it exists when you multiply by z minus z0 to the power of k. So let's just look at something very, very basic for now. So if we have something like 1 over z, then, okay, obviously 1 over z has a singularity at z equals to 0. So the limit as z goes to 0 does not exist. Right? So the limit here does not exist, but the limit exists if I first multiply it by z. So if I first multiply this by z, then we will get 1, and in that case the limit would exist at 0. And so in that case we will say that this has a pole at 0 of order 1. So it has a pole of order 1. Because when I multiply it by z, then the limit now exists. But if I don't multiply by z, then the limit does not exist. So essentially what this definition is saying is that we have a pole of order n if n is the smallest integer for which this limit exists. So if you have a k that's smaller than n, then the limit does not exist. So it's order n pole if the limit exists, or if n is the smallest number for which this limit exists. Okay, and finally, if this limit doesn't exist for anything, then well, we have an essential singularity. So a typical question is, okay, we're not there yet. Yeah, so yeah, this is pretty much the same as before. Skip that. Okay, so classify the singularities of this one. So first of all, we just need to find like where is this function not holomorphic? Well, it's usually just this thing at the bottom. So z squared sine z. Where is there an issue here? Well, clearly if z is equal to k pi, then the function is not holomorphic. because when z is equal to k pi, then we know the sine z is equal to 0. Okay, now we're going to classify them. So obviously they're not all the same, because actually there is also a z squared here. And we know that z is 0 when z is 0. So actually, here we probably need to treat z equals 0 a little bit differently from the other values of k pi. So it turns out that when z at 0, it turns out that f actually has a pole of order 3. How do we know this? Well, I guess like if we multiply f by z cubed and then take the limit, we find out the limit exists. Whereas on the other hand, if you only multiply f of z by like z squared, then the limit does not exist. So if I multiply by z squared, I get rid of this. I have 1 over sine z. Clearly, the limit does not exist as z goes towards 0. So most of the time, just by looking at it, it's fairly clear that there's sort of like 3 zeros here. There's a z squared, so that's like 0 twice, and there's a sine z, which is another 0. So you can sort of think of it as like there are 3 zeros for the denominator, and so it should have a pole of order 3. And here we do in fact verify that the limit exists when we multiply it by z cubed. Whereas if we multiply by z or z squared, the limit doesn't exist because the bottom would be going to 0. So that's for 0. Now for the other ones, so for the other k pi, we'll do the same tactic. So based on the formula we had before, one of the easiest ways to evaluating a pole is that if we multiply by z minus z0 to the power of k, we need the limit to exist. So it turns out that for k pi, if we now multiply by z minus k pi, then we do some stuff. This is just using the L'Hopital's rule. We see that actually the limit exists. The limit exists, and so we say that it has a simple pole, so a pole of order 1. The pole of order 1 meaning that if I multiply by this thing to the power of 1, then the limit exists. Whereas here this was order 3 because I had to multiply by z to the power of 3 in order for the limit to exist. Okay, so this thing has it has simple pole everywhere, all of the k pi's except for z equals 0, where it has a pole of order 3, or a triple pole. Okay, and then slightly different question, calculate the singularities for this one. So again, this is fairly similar. Again, we want to look at the bottom and see like where is this thing not holomorphic. Well, again, it's at k pi. Oops. So k pi is where we have issues. But this time we see that on the numerator there is the z is a 0 and pi is a double 0. So I have to be a bit careful about that. So actually, I guess like by now we can sort of see it like 0 is like a double 0 for the denominator because we have sine squared. So 0 is like a double 0 of the denominator. But the z is also a 0 of the numerator. And so overall, this is actually a simple pole. And you can verify that if I multiply this by z, then the limit should exist as z goes to 0. And using a very similar idea at pi is like a double 0 of the numerator, and it's also a double 0 of the denominator. So overall, it should just be a removable singularity. And again, you can verify this. You can verify using calculus that if I take the limit as z goes towards pi, the limit should exist. And every other singularity we have, well, they are order 2 because they are all double zeros of the denominator, but they are not zeros of the numerator. So all of the other ones are order 2. Again, you can verify this if you want. Okay. This one here, classify the singularities. We'll probably skip that since we don't have so much time, but you can have a read of this afterwards. Okay, so more importantly is to actually calculate residues. So as I said before, like Cauchy's integral formula or the generalized integral formula, those are really just like actually specific cases of this. This actually helps you evaluate a lot of things beyond what those allow. So if there's one thing to remember, it's this one. So, okay. First we need to find the residue. So actually, the residue at a point z0 is simply the coefficient of that. So, so if I write the Laurent series for a function, and my computer's messing up. Okay, so if I were to have the Laurent series about z0, then the residue at z0 is simply the coefficient of c negative 1. So it's really just the coefficient of the term z minus z0 to the negative 1. That's what the residue is, by definition. But usually, like let's say like 80% of the time, the exam questions are not going to get you to do it in this way because usually there's a simpler way, which is in terms of limits. This formula here. So actually, if I want to evaluate the residue of the function at z0, usually I need to evaluate this limit. Typically, if the pole is of order n, so if n is equal to 1, this is very simple. If n is equal to 1, then this thing goes away, this thing goes away, and this is just 1. Okay, so typically if it's a pole of order 1, it's simple. That's saying that you just need to multiply your function by z minus z0, and then take the limit as z goes towards z0. So I guess that's why this formula is convenient. So often it's easy. So if the pole is of order 1, which happens most of the time for exam questions, if it's order 1, this is all you have to do. Multiply by z minus z0, take the limit. Now, if the pole is of order 2, then depends how the function looks like. If the function looks nice, if it's something that you don't mind differentiating, then yeah, differentiate it once. But usually if the function looks bad and n is equal to 2, or even worse if n is larger than 2, you actually probably don't want to use this formula because differentiating this is, well, it can be quite bad. So I guess that's up to you to make your judgment, like is this the best way to do this question, or do you just want to use the definition of the residue, which is to compute the coefficient, c negative 1. So in the next few examples, we would see examples of using both methods to calculate it. So yeah, this is a function we had from the previous example. I think this is actually in your tutorial problems. I think I just picked a random question from there, and actually this question turned out to be very annoying. I think this question took, I think you'll see here that I have like 3 or 4 pages, or 3 or 4 slides to actually explain this question. It turned out to be very annoying. But I couldn't stop because I have gone too far already. Okay, so pretty much from the previous question, we saw that this function here has singularities at z equals to k pi, where for k is equal to 0, we have a simple pole. For k equals to 1, we have a removable singularity, and for any other value for k, we have a double pole, or a pole of order 2. Okay, so I want to calculate the residue at these singularities. So we'll first start with the easy one. So z is equal to pi, this is a removable singularity. If it's a removable singularity, then the residue is just 0. Because a removable singularity means that this function here already can be written as a power series. And if it can be written as a power series, that's saying that the coefficient of the the negative indices is just 0. So this is true in general. For anything with a removable singularity, like for anything that is holomorphic around that point, then the residue is just 0. Okay, and z equals to 0, this one is a simple pole. So if it's a simple pole, as I said, we probably want to use this formula because when n is equal to 1, most of the ugly stuff goes away, and that's saying all I have to do is multiply by z minus z0 and then take the limit. That's precisely what's happening here. So it's at 0, so all I need to do is I multiply it by 0 and then I take the limit. So I multiply by 0, I get this guy, I take the limit. this should be fairly simple to do because we know that this thing here goes towards 1, z goes towards 0, so this is just 1. Oops. So this is just 1. And over here, I can just sub in 0, so I have 0 minus pi, I square that, we get pi squared. Okay, that's pretty okay as well. Okay, so finally, k pi, when k is not 0 or 1. So you could, of course, use the formula that we just had, do this. So in this case, we have to differentiate it, and then you have to differentiate z minus k pi squared multiplied by g of z. And unfortunately, this is horrible. Well, this is g of z. And here we're actually multiplying g of z by this thing. That is quite horrible. You have to multiply them together and then differentiate. I assume none of you want to do this. When I was looking at this question, I put it into Wolfram Alpha to see what I got. And I feel like Wolfram Alpha's computational time exceeded or something like that. Or at least for some of the other calculations they were trying to do. So yeah, you probably don't want to differentiate it. So instead, we need to use the other method. So instead, we need to go back to definitions and find the coefficient of, we want to find c negative 1, which is if we write a Lorentz series centered at z0, I want to find the coefficient of z minus z0 to the negative 1. So this is what we will now attempt. So we now want to find the coefficient of, okay, we want to find c negative 1 for the Lorentz series centered at k pi. Okay, so the way we're going to do this is we're going to make use of Taylor series because that will make things easier. So this is the Taylor series for sine squared z minus k pi. And obviously, you can get the Taylor series for sine squared z. That's on the denominator. But I noticed that sine squared z, we can just rewrite it like this. The reason we do this is because now we get a power series that is centered at z minus k pi, which is exactly what we want. That's why we did this. Sort of a trick here. Okay. But the problem is that sine squared is on the denominator. So now this looks quite ugly. I agree with that. I had to type this up. It was not very fun. But okay, so this is another technique that you can use. So this is actually, if you know the Taylor series for something, then you can actually find the Taylor series for the reciprocal of it. Or at least you can find the first few terms, which is what's happening here. So this thing here, I have just dumped it down here. I have just written it out term by term to make it a little bit easier to see. So I write out term by term, and then what I do now is I take out z minus k pi squared. So I take that out from the bottom, and then now we get this. But what we recognize is that, well, this is once again in the form of 1 over 1 minus r. So I can rewrite this as a sum. Okay, I realize this is missing a square. But basically, I can rewrite the thing inside as a summation. The r is this huge thing in here. This thing is my r. So I can rewrite it as the sum of, so I can rewrite it as sum of r to the n. That's exactly what I'm doing here. So whenever you have a Taylor series, I can always write the reciprocal of this Taylor series in this sort of way. So here there are a lot of terms, but actually I don't care too much about these terms because most of these terms are like higher powers. I actually don't care. So what we really care about is just this term. Let's just make this a little bit more clear. So essentially here we have got a lot of higher order terms, but we don't care about it because in this question we're trying to find the coefficient of this thing to the negative 1. We are trying to find c negative 1. So if we're trying to find c negative 1, I don't care about all of these higher powers. I only care about the terms that actually have a negative index. And so even though there are lots of terms in this expansion, there is actually only one term I care about, which is the first term. And the first term is 1. Right? The first term is I is equal to 0. If I put I is equal to 0, the first term is actually 1. Every other term has a higher power. I don't care about those, because if they have a higher power, they're not going to influence the C-1 coefficient. So the only term I care about is when I is equal to 0, which is 1. That's what we have here. So this is the only term that we care about. So going back, this is our sine squared z. So I have found 1 over sine squared z. Well, if we now multiply by the thing on the numerator, we get this. And so the goal is the same. What we just want to find is the coefficient of this, and that would be the residue. So one way you can do this is you can expand this entire thing, and then you can do like a, you can do that entire thing, do a division, do a polynomial division, and you just need to find the coefficient of this. Basically, I have done all of that for you. This is basically just, I've basically just found the coefficient of this guy after you expand and do everything. You guys can check this out later, but essentially this is just some algebraic manipulation. But in the end, I'm just finding this coefficient in this fraction. And if you check it out, you should end up getting this. Okay, so pretty much that was a lot of work, but in the end, we find that this is the residue, because this is the coefficient of that. So this is the residue, and as a sanity check, actually, if we sub in k equals to 0 or 1, we should obtain the same answer as we did earlier. So if we sub in k is equal to 0, we get a residue of pi squared. And pi squared is precisely the residue we had here. And if we sub in k is equal to 1, we get 0, which is precisely the residue we get here. So at least once I get that, I know that I did it. It's likely that my answer is correct. But yeah. So I guess like generally this question would have showed this idea of like calculating residues. Usually you want to use the formula with the limits, but if it's one where if it's a higher order pole, then you can't really evaluate the limit easily. You would need to, because you have to differentiate first, and in which case you want to try to find the Lorentz series, where we only really care about this single coefficient, so you can sort of ignore the other things, which is what I've done here. I've ignored all of those annoying terms in this crazy expansion because they don't matter. Okay, hopefully I didn't miss out on an easy method to do that question because yeah, it took me a lot of time to write up. Okay, so last thing we have here is the Cauchy's residue theorem. So this is probably the most important thing today. Most of your exam questions would require this theorem, like not most of the questions, like every exam would probably have like a big question in question 4 that's just focused on this residue theorem. So this is saying that if I have a, again, it's a simple closed contour, then if I have some finite number of points inside, so if there are a finite number of points inside where f is not holomorphic, then it turns out that we can actually evaluate the integral by simply evaluating the residue of the function at each of these points. Right, so if I can find all of the points inside this contour where the function is not holomorphic, then I just need to evaluate the residue at each of these points, sum them up, multiply them by 2 pi I, and we get the integral. So now you probably see that the Cauchy integral formula or the generalized integral formula, those are actually just special cases of this one where you only have a single point where it is not holomorphic. So this is like more general because we can account for having many of these points inside this contour that are not, where f is not holomorphic. Okay, so pretty much this is very useful. If you just if you just remember this one, you don't really need to remember the Cauchy's integral formula unless they decide to ask you to quote the theorem. But this can do every question that the Cauchy's integral theorem can. Okay, yeah, this is a question taken from past exam, hopefully long ago enough that I'm not going to spoil your past paper practice, 2015. So, okay, so first part I can go through quickly is just to find all the singular points, classify them, and find a residue. So hopefully we've already done that. So singular points, this is where there are issues, so this is where the function is not differentiable. So obviously 2 is a problem, -2 is also a problem, and then 0 is also a problem. So the singular points, 2, -2, 0. Okay, classify them. We can see that 2 and -2 are both zeros of the bottom, but they are not double zeros or whatever. They are like single zeros. So they are both simple poles. Okay, so they are simple poles, and to calculate the residue of simple poles, we just need to use the formula where we multiply by z minus 2 and then take the limit, and we are done. We'll do the same thing here. We multiply by z plus 2 and we evaluate the limit, which should be pretty easy. Evaluating the limit here is super easy because you just need to basically cancel it off from the denominator and then sub in whatever the value is. Okay, and finally, z equals to 0 is an essential singularity. So for essential singularities, obviously you can't use the formula to you can't use the limit formula to evaluate it. You actually need to find the power series and then find the coefficient, which I guess you certainly could find it here. I guess the question doesn't say. The question just says find the residue at each pole. I guess that's not a pole, so we don't need to find the residue. But if you were to do it, you just need to, well, I guess it's a bit harder here, which is why they didn't ask you. Because you have to find the power series, you need to find the Laurent series of this function, and then find the coefficient of z to the -1. That will be the residue of 0, but it's much harder to find. Okay, so part B is to explain why this integral here is 0. So, as usual, if you ever get these questions about like integrals equaling 0, like some contour, usually the thing that we need to use is the ML lemma. We already saw one of these questions earlier today. Okay, so we need to use the ML lemma. So, oops. Okay, so gamma r, this is a circle centered 0 with radius r. So once again, the ML lemma states that the modulus of the integral should be less than or equal to the length of the contour, which is 2 pi r, multiplied by the supremum of the integrand. So in this case, the integrand is this. Okay. So I didn't just change it to r for like for no reason. It is actually true. This is based on well, I guess that you can prove this. In your exam, you'll definitely prove it. Here, I just skipped it. But basically, you can actually show that. I'll very quickly like describe like roughly what you would do. So if we're trying to find the modulus of this one, this is equal to this sum. So k factorial z to the k. And then based on the triangle inequality, we know that this would be less than or equal to the sum of the moduli. Okay, Mac is playing up. Okay, so we get this. But we know that the modulus of z is r because this is a circle, and so this is simply e to the 1 on r. So it is actually, in fact, true that this numerator is less than or equal to e to the 1 on r. And if you do some of the other, if you use like the circle inequality or something like that, you should also be able to see that the modulus of z squared minus 4 should also be greater than or equal to r squared minus 4, which is why I can change the denominator as well. Okay, so I guess you can verify this if you're not convinced, but yeah, basically I've checked it out and it's true. Okay, so if we use the ML lemma, we get this, and all we need to do now is to take the limit as r goes towards infinity. This thing should be obvious because when r goes to infinity, 1 over r is just 0, and so this thing here is just 1. And so essentially we're just calculating the limit of r divided by r squared minus 4, which we obviously know from first year calculus should be 0. Because r over r squared minus 4, the denominator has a higher power. So that's going to 0. Okay, so once again, we're using the pinching theorem. We know that this thing here is obviously greater than or equal to 0. This is greater than or equal to 0, and the upper bound is also something that's going towards 0. So by the pinching theorem, we know that the modulus of the integral is going towards 0. And we also know that if the modulus is going to 0, that means that the thing inside itself is going towards 0, using some of your limiter theorems. Okay, and that's what's required. Okay, and the last part of the question is to calculate this integral. So this time gamma 1, so that means that for the unit circle. Now, if we think of Cauchy's residue theorem, this is saying that it says that this should be equal to 2 pi I. Actually, let's get back to that. So this is saying that it's 2 pi I times the sum of the residues applied at all of those points where it is not holomorphic. Here, be a little bit careful because we have the unit circle. So we have the unit circle. The points where this is not holomorphic are -2, 2, and 0. So actually, the only residue that we are interested in calculating here is actually at 0. So this is 2 pi I multiplied by 2 pi I multiplied by the residue at 0. But that's the only one we haven't calculated. In part A, we were able to calculate the residue at plus or minus 2, but we said that we couldn't calculate, we didn't calculate the one at 0 because it's a bit more annoying. You have to find the Lorentz series, which is quite hard. So once again, it's an exam question, and exam questions are written in a way that students are meant to be able to do them. So usually the technique is just to think of and the question even says hence. So I guess you need to figure out why hence? Why is it relevant? Well, the previous question is saying that as r goes to infinity, this integral should go towards 0. Well, but we also know that for large enough r, in fact, if r is greater than 2, then obviously all three of these singularities would be in the interior of this contour. So actually that's saying that 0 is just equal to 2 pi I multiplied by the sum of the residues. The residues at plus minus 2 and 0. So actually I can use part B and part A to work out what the residue of f at the point 0 is. And then I can use that to evaluate the integral. That's essentially what's happening. So from the residue theorem, for r, whenever r is greater than 2, all three of those singularities would be in the interior. And so we have this. But from the second part, we already know that as r goes towards infinity, this thing is going to go to 0. So in fact, we have this expression, and we already know what the residue at 2 and the residue at -2 are from part 1. And so if I substitute those values inside and rearrange, just believe me, we would get this. So essentially here we have evaluated the residue at 0. Alternatively, you could have calculated the power series, the Lorentz series yourself if you wanted, and you found the coefficient of z to the -1, it should also equal to this. I guess for those of you interested in bashing out very, very big Lorentz series questions, then yeah, you can have a go and see that you can actually get this as a coefficient. But okay, Otherwise, we can just use Cauchy's residue theorem again. This time we apply it to the unit circle as the contour. As I said, plus or minus 2 are not within the interior, and so I only need to have the residue at 0, and I substitute this thing inside, and we'll get this, and we are done. Okay, so I think this is the second last question we have here, and one more and then we'll be done. Okay, so once again we have a function. We want to find all the singularities and classify them. I guess we'll do that first. So as usual, singularities, I want to find where is the denominator 0. So this is reducible to a quadratic. I can very easily solve it. Okay, so I factorize it further, and we get the 4 roots. So these are all single roots. They're all single roots of the denominator. Obviously, the numerator itself doesn't change anything. So these are all, in fact, simple poles. So there are zeros of the denominator of order 1. They're all simple poles. Okay, we also need to find the residues. Okay, well, residue is very easy. All I need to do is multiply by z minus z0 and then take the limit. That's all I need to do. But I also only want the ones that lie inside the unit circle, so I'll only deal with these two. I will ignore this one, I don't care. It's not in the unit circle. So I want to find a residue, so if I want to do that, I need to first of all multiply by z minus 1 over root 2, and then take the limit. This is quite easy to do, right? Like, I think I didn't write out the full working, but the bottom here we can factorize it, and all we need to do is multiply by z minus 1 over root 2, in which case like one of the factors is going to disappear. Once that has disappeared, you can just sub in 1 over root 2 directly into the expression, and you should get 1 on 6. Again, you can check this, and do the same thing with negative 1 on root 2, and we should get 1 on 6 again. Okay, so finally we want to evaluate this integral. So yeah, obviously it's somehow related to the previous questions. So on the previous part, we've evaluated all of the singularities. The question tells us the unit circle. That probably means that I want to evaluate this. The fact that I already know what the residues are means that I am able to evaluate this very easily using the Cauchy residue theorem. And once I calculate this, I should be able to somehow convert it into this one, the one that we're trying to find, because they are very similar. Because if gamma represents the unit circle, we can actually just if gamma represents the unit circle, well, we can actually just convert this integral into the one on the left. So that's exactly what we're doing here. So based on Cauchy's residue theorem, I can evaluate this integral very easily. Like this, equals 2 pi I on 3. So we already calculated each of these as 1 on 6, 1 on 6. So we have, this one over here. So I just made a substitution. And if I now make the parameter, if I now use this parameterization, z equals to e to the I theta, well, as usual, I'll just put it in. So first I will manipulate it a little bit. So this is the integral that we already know. So this integral here is 2 pi on 3i. So I'm just going to first manipulate it a bit to make it easier to make this substitution. So what I did is I divided by okay, so I divided by z on the top and bottom. Yeah, so I divide by top and bottom by z, and then I do some factorization, and we should get this. The reason being now I can substitute this in very easily because we know that z plus z to the negative 1 is in fact just 2 cos theta. So I think some steps were skipped here, but this is just 2 cos theta. So 2 cos theta. And so we're going to square it and then multiply by 2, we get 8 cos squared theta. And the other thing we note is that when we have dz equals to I e to the I theta. That's where this thing here comes from. And the bottom we have z e to the I theta. Okay, well, things cancel off, and we end up getting this. So this is exactly what the question wants us to find. We already know that this integral is equal to this. So I can just cross off the i's, and we know now that the integral the question wants us to find is in fact just pi on 3, 2 pi on 3. Okay, yeah, one final question is if they just give you an integral out of nowhere and ask you to solve it. Actually, this is not much harder. All you really need to do is to convert the cos and the sine thetas into z. Almost all of the time, you're just looking at the unit circle. There's no point looking at any other circle because they're just different by a factor of a constant. So typically these questions, it's a unit circle. So I want to make the substitution z equals to e to the I theta. Well, if I do that, then with the usual thing, and then I just need to rewrite the cos to theta and rewrite the cos theta in terms of z. So you need to remember your identities. Cos 2 theta is in fact just z squared plus z to the negative 2 divided by 2. Cos theta is in fact just z plus z to the negative 1 divided by 2. So I just substitute them in. I convert them all to z. Make sure that you don't miss this term because I need to change the we always have to do this whenever we're doing a change of variable from theta to z. But otherwise, we just need to, well, simplify the algebra, simplify it a bit to make it into a form that looks nice. And this looks pretty nice to me. Okay, so essentially I just now change this complex integral into something that looks, well, I guess it doesn't look simple, but this is useful because we can actually solve this one quite easily using the Cauchy's residue theorem. So we just need to find where the zeros are. So there's negative half, there's negative 2, and 0. But actually, we don't care about the negative 2 because, yeah, because the negative 2 is outside. Negative 2 is outside of this unit circle. We don't need to care about it. So we simply need to evaluate the residues at 0 and negative half. So as usual, if I want to evaluate at negative half, that is a simple pole. It's a 0 of order 1 on the denominator. It's a simple pole. All I need to do is multiply by z plus half and then take the limit. Whereas z is equal to 0 is a bit harder because this one's actually a double pole. So if you want to use the formula, if you want to use the limit formula, you have to differentiate. I still do think that's probably the easiest way in this question. So you would see here that I have differentiated it for you. I didn't write out the full stuff, but yeah, you can check this out yourself. If you differentiate this expression, which is not too bad, if you differentiate it and you sub in z equals to 0, you should get negative 514. Yeah, you can check that out. It's just a bit of work. Okay, so we have the residues at each of those points. And then using Cauchy's residue theorem, I just need to have 2 pi I multiplied by the residues added together. This 1 on 2i comes from the previous page. We have 1 over 2i. Okay, and we get a final answer of pi on 6, which is what the question required. I think as generally you would probably expect to get like a real answer because these are real values. If you ended up with an I somewhere in your final answer, I would be pretty suspicious about that, and you would check your working out and make sure that you have not made a mistake. Okay, yeah, that was a pretty long seminar, I guess. Yeah, hopefully everyone learned something today. As I said earlier, the 2621 exam I think is one of the hardest exams I have done, one I did last year. Even though it's a 3-hour exam, I thought it was pretty ridiculous. Yeah, it's pretty much one of the only exams I've done pretty much one of the only maths exams I've done at uni where there were like a couple of questions I couldn't do. But don't worry too much about it. There's probably going to be scaling to adjust for it. So I think generally it will be a fun exam. So good luck to everyone. And yeah, if anyone has any questions, just let me know now. Otherwise, I'm probably just going to end the stream.